right, let's walk through the warm-up. Well, let me see if I can adjust this screen. Come on. Go. No. Well, I'll just pull that down. Okay, so parameterizing the boundaries is the hardest part. So for those of you watching the video, we did this warm-up. Everyone started on it for quite a while, and then I gave the parameterized versions of the functions. Just know that your WebAssign and most of your problems, the parameterized versions already give it to you. But anyway, so for the first one, and that's your function, 2x plus y. So the first one, tt, you have to replace x with t and y with t times the arc length of the function from 0 to 1. So remember that it's x prime squared plus y prime squared. So 1 squared plus 1 squared. So you get root 2. This is me right. It looks like I wrote out the entire thing in one big gigantic problem. So this is C2, which has an x of 2 minus cosine t and a y of 1 plus sine t from 0 to pi. So replace arc length, square, square. Next one, 2 cosine t plus 1, 2 sine t plus 1, arc length. And then the last one, just t negative t with your arc length from -1 to 0. Just make sure that all of your t's are going low to high. So as long as they're going low to high, it's fine. If they're going high to low, we've got issues. So make sure they're going low to high. Yes, Tejas?
Could you explain how you got the boundaries for C2 and C3?
So kind of a guess and check kind of a thing. I remember when I was first trying to figure this out last year, because I am not good at writing an equation of a circle in polar when the center has been shifted. But then I started thinking, well, it's going to be some sort of an r cosine theta, r sine theta, and I know I'm probably going to go from like 0 to pi, right? Because that's kind of what it looks like. So then I thought to myself, well, if I have this one as an r cosine theta, and I want it to start at the point 1, 1, right, where I plug in a 0 and I get out a 1, well, that could be like a cosine theta, right? And then my sine theta plus 1, something like that, right? And then I had to figure out what would I get. You kind of do like a little system of equations, right? So like if I had let's see, the radius is 1, so it would just be cosine theta plus a, or cosine theta plus a sine theta plus b, or something like that. Just set it equal to 1, 1, set it equal to 3, 1, and see what you get. But it's not a big deal. It's not like this comes up a lot, but that's how I did it. I kind of guess and checked it, but I think you could do it pretty, like, reasonably with a system. So, because you know the radius is 1, right, on the little circle.
Yeah.
So you can kind of use that automatically and then just kind of figure out what you have to add or subtract in order to get it to work right. You know the radius is 1, and you know you're probably going to go 0 to pi, right? So anyway, so that's how I did it. All that setup, and then your final answer was root 2 plus 10 plus 11 pi. I don't have, let's see. I wonder if each of these is an individual answer. It looks like the first one, 3/2 root 2. The second one, the 5t plus 1 plus, or 5 pi plus 1 plus 1. And then I think that's the third one. And I think that's the fourth one. I'm kind of guessing right now.
Yeah.
But that's what it looks like.
Yeah, I'm pretty sure that's right.
Yeah. So, look, I see a negative root 2 over 2. I see a 3 root 2 over 2.
I screwed up the second one.
Okay. So I see some, like, you guys like the first one and the last one, right? It was those middle ones that are tough. This one's really close. Wow. Okay. So 5 pi plus 2. Look at that. And, yeah, there's the 3 root 2 over 2. root 2 over 2, negative root 2 over 2. Yeah, a lot of you guys got the first and the last, which means that you get the process right.
No, I forgot the double thing.
Some of you guys didn't convert to polar for the second and third, and it was crazy.
Oh, yeah.
We'll have to solve it. Yeah. Yeah.
So that would have been,
Yeah.
that would have been it.
All right, that's okay. Today we're doing surface integrals, 16:7. I have to remember that the recording is not going all the way up, so. Oh wait, there we go. I can move it up. I just can't make it go down. We're spending 2 days on surface integrals. Today we're basically just learning how to evaluate, how to set them up and evaluate them. And then tomorrow we're learning an application called Flex. You will learn 2 types of surface integrals. You're going to learn surface integrals for regularly defined functions with x's and y's and z's, and then you will also learn how to evaluate surface integrals for parametrically defined functions as well. Okay, so a surface integral essentially gives you the mass of a surface. So we've kind of done this before, where it's kind of like, I don't know if you remember where we found mass by doing the double integral of the density function. Same kind of thing, double integral of the density function. So the first part's going to be almost review because we've done it before, but we haven't done it with parametric functions. But it's important that we understand what a surface integral is. And the way that we're going to evaluate it in the context of kind of expanding on line integrals is we're first going to do them with respect to essentially surface area. So, and by the way, if there is no integrand here, if it's just 1, then the double integral actually gives you the area of the surface, right? So this would be density. Basically, if the density is just 1, you're just getting a surface area, right? Okay. So, evaluating a surface integral, let S be a surface with equation z equals g of x, y. Let R be its projection onto the xy plane. If g sub x, and g sub y are continuous on R, and f is continuous on S, then the surface integral of f over S is the double integral over S of your function ds, which essentially is the double integral over the region R, which is the reflection down onto the xy plane. You just set your z equal to 0, and you do the double integral that gives you the area of your, whatever your integrand is. No z though. You just replace the z, solve for z in terms of x and y. So it's your integrand, and then times square root of 1 plus g sub x squared plus g sub y squared dA. Where A is the area of region R. It looks complicated, it's really not bad. Now, there are 3 ways to orient a surface. So I put all 3, but I want you to understand it's the exact same formula, just from different perspectives. So this is the main formula. This is kind of if your surface equation, if your region R is projected onto the xy plane. If your surface equation is a z in terms of x and y, and your R is on the xy plane, that's this guy. But you might have a surface that's sideways. And if you have a surface that's sideways, it's the same thing. So here's the xy plane. This is if you're projecting onto the xz plane, and this is if you're projecting onto the yz plane. Everything's the same. You're just using the variables like according to what you're given. So if we're projecting onto the yz plane or the xz plane, it means we're going to solve for y in terms of x and z, and then you're going to do partial x and partial z. And if you're projecting onto the YZ plane, it means you're going to solve for X in terms of Y and Z, and you're going to have partial Y and partial Z. So it just depends on which way you're projecting. I'm pretty sure that your book, that your homework tonight is all projecting onto the XY plane. I can't think of any that are turned sideways. I skimmed through it. I didn't work the problems, but I can't think of any that are turned sideways. But this is there just in case you need it. I'm going to pause. Okay. All right, so we're going to do an example. Evaluate the surface integral below where S is the first octant portion of the plane, 2x plus y plus 2z equals 6. And the integral they're asking us to evaluate is the double integral over region S of y squared plus 2yz ds. So there's a couple things that you have to do. So we're going to go ahead. This is first octant portion. I'm going to solve this for z. So everyone take a second and solve this for z. And get your z, folks. You can do this. Solve that. 2x plus y plus 2z equals 6 for z. Okay, so that's the equation of the plane if you were to solve it for z. And now, when you rewrite your integral, so without putting in limits yet, so your y stays y, but your z now becomes that guy right there. Yes?
How do you know if it's being projected on the XZ plane, YZ plane, or XY?
This one, you could go anywhere, because you're gonna get, well, there, you know what? There's no x's.
Wait, could you just do like the FC and then you would have to, or YZ and then you wouldn't have to do like anything?
And you wouldn't have to do anything. We should try that.
Yeah.
I just always solve for z.
Wait, what?
But if we solve for x,
Oh.
then there's no plugging in. That's kind of nice.
Whoa.
And it really is just the mass of the surface, and it's the same surface, right? Although, okay, and then you'd have a little trick of figuring out, well, no, it wouldn't be that bad for your y plus 2z equals 6 and your x equal to 0 and finding your projection onto the yz plane. Do you want me to scrap what I've got and we do it with the yz plane? And we see what we've got? Okay, so here's what I'm going to do. I'm going to keep what I have, but I'm going to move it down. Is this attached? Yeah, there we go. So that we have some space. Oh, we're going to get one of these weird things. That's okay. And then we're going to find the answer and compare and see how we do. All right. It'll be fun. It'll be like a big experiment. All right. So backing up, solving for x. So you get 1/2 times 6 minus y minus 2z, right? Okay. So you need a couple things. In order to find your limits, you have to draw the projected image into whatever your plane is. So in this case, we're going to project onto the YZ plane. So if you want to think of it as like YZ, so you set your x equal to 0, and you get y plus 2z equals 6. So z equals 1/2 times 6 minus y. So it's 3 minus 1/2 y. So we have an equation like that. And this would be 3. So if y, yeah, this would be 3 this way, and this would be 6 that way. Right, there's our triangle. I did my math right? I think I did. Okay. All right. So then when we set up our integral, so we're going to have a dy dz, or dz dy. It really doesn't matter. So if this is the equation z, I'm going to, since it's solved for z, 1/2, so 3 minus 1/2 y. All right. So I'm going to have my z's go from 0 to 3 minus 1/2 y, and I'm going to have my y's go from 0 to 6 to produce my triangle. Then my integrand can just stay what it is. And then I multiply by my root, which is 1 plus, and then it's partial y, so this is technically negative 1/2, right? Squared plus, and then partial z, which would be negative 1 squared. Whoops. Yeah, no, dz dy. Plus 2. All right, what do you think? Did I do my setup okay? Yeah? Okay. All right, let's evaluate. I'm just going to clean this up a little bit. So let's see. 1 plus 1 is 2 plus a fourth, so 9/4. So, oh, that's nice. It's just 3/2. Yep. Whoops. I'm going to move this down and then make it marks.
So this price,
Yes.
theoretically, you can use whatever like thing that you want, right?
You know, some are going to be like really crazy though. Like if you have a surface that is going like this in this direction, you're not going to want to try to project it this way. So if there's overlap. So you're going to want to project it into a plane where there's no overlap, no plus and minus-y kind of stuff going on. But I guess like mass is mass. I never really thought about it. Like you guys are the first class to suggest, hey, let's try it on a different plane. So this is my first time. We'll see what happens. Okay. All right. All right. So first dz, so we have y squared z plus y z squared. I'm going to put the 3/2 out front. Let's see. Oh, evaluated from 0 to 3 minus 1/2 y. Y. So let's see, those are z's. So I have y, I'm just going to distribute. So I have 3y squared minus, let's see, 1/2 y cubed plus y times that squared. I'm going to have to square it out because I don't have a y times a y. So 9 minus 3 halves minus 3 halves, which is minus 3y plus 1 fourth y squared. All right, minus 0 dy. You guys getting the same thing? Are you even doing it? Is everyone just waiting?
I know.
Okay. Oh, look, I even wrote this down. If you got this on the other planes, you'd get the same answer. So, looks like I thought about it, we just didn't do it. All right, so, cleaning up. All right, 3y squared minus 1/2 y cubed plus 9y minus 3y squared plus 1/4 y cubed. Well, this is going to clean up nice. If I did my math right. So, equals 0 to 6. So, negative 1/2 plus 1/4 is negative 1/4 y cubed plus 9y. All right, let's integrate. Go away. So, 3 halves times. So, negative 1/16 y to the 4th plus 9 halves y squared, evaluated from 0 to 6. All right, so we have 6 times 6 times 6 times 6 over 16. So 3, kill 2 and make it 8, kill 2 and make it 10, kill 2 and make it 4. So another 2 2's. So it's 81. Okay, so negative 81 plus 9 times 18.
162.
What is it?
162.
162. Thank you. Minus 0. Oh, so it's just 81 times 3 over 2. So 243 halves. Did I do my math wrong?
That's what I got.
Let me see if that's what I got the other way. Yeah. Woo. They both look like they're really not that different from each other. Honestly, it's not like this one went, wow, was this easy, right? I don't think it made our lives that much easier, but that's okay. Let's do, I think I have one more example, I do. And then we got to do parametric because that's really the new stuff today. So evaluate the surface integral below where S, this one I did orient sideways, and this one would be where they're telling you, let's see. So S is the first octant portion of the cylinder. So y squared plus z squared equals 9 from x equals 0 to x equals 4. So in 3D, x equals 0. Oh my gosh, I don't know how to cut it out. But like think 1, 2, 3. We're coming out this way, right? So we're going like from the y-axis. So bad at 3D imaging. We're getting this hunk there. That's what we're doing. Because it's from x equals 0 to x equals 4, the region of the cylinder in the first octant. Okay, so it's a sideways oriented cylinder. It's y squared plus z squared equals 9, right? Okay, so this is like that's 3, little radius here is 3.
Which one's X, Y, and Z?
So that's X, Y, Z. Okay. So note that this can be projected onto the XY plane or the XZ plane, but not the YZ plane. Why can't it be projected onto the YZ plane? Exactly. You just end up with nothing but a line, right? That's that 3D spatial reasoning skill. Yeah. It wouldn't work. So you can do XY or XZ, whichever one you prefer, but you can't do YZ. So do you want to do XY or XZ? I'm going to see which one I did. I did XY.
Let's do XY.
Okay, we're doing XY. So if we project this onto the XY plane, then everything has to be in terms. So think of it as like your projection is if you took all of these ordered pairs and made all the z's 0, so you end up with this like that flat area on the XY plane. All right, so there's our projection onto the XY plane. So that's what's going to help you get your limits set up. And then your integrand, there's your integrands. See what you can do with it. Play with it for a minute. Just see if you can get an initial setup. So XY plane means you're going to have to solve for Z. So what your limits, your x is going 0 to 4, your y is going 0 to 3. You get your y's by setting your z, just set z equal to 0, and you get y squared equals 9. So y is bounded between -3 and 3, except we're in the first octant, which means that y is just going to go from 0 to 3. So there's your y's, your x's are given 0 to 4. The only other thing you have to do is convert your z in here to a root 9 minus y squared, and you have to find some partials, right? So partial x is 0. Partial y takes a tiny bit of work, so it's like you'd have blah, blah, blah. Anyway, negative y over root 9 minus y squared. All right, so that's just showing you the boundaries. So your integral setup would be integral 0 to 4, integral 0 to 3 of x plus that's your z, square root of 1 plus z sub x squared plus z sub y squared, and then dy dx. What'd you forget? Forgot the 1? I don't understand this philosophy of destroying up the whole sheet because you forgot the number 1. Like, can't you just stick a 1 plus in there?
I just want to look after that as a point.
There really is a point. Sometimes there's a point.
That's the wrong point.
All right. Okay.
Just scribble on his paper and throw it away.
All right, so clean it up.
I misspelled calculus. Gotta throw it away. That's literally take that job.
And remember, root 9 is just 3. So I distributed. You get 3x over square root of 9 minus y squared plus 3. Ooh. Antiderivative.
Oh, that's like.
Wait, how did
Are you serious?
Not arctan, it's arc sine. Arc sine. It's been a while since we've done an arc sine antiderivative, right? So do you remember? I don't know if you guys remember. It was a 1 over a arc thing x over a, right? Except arc sine, I used to say sine is like sine, which means without because it doesn't have the 1 over a in front, right? And then the secant is the one that has an absolute value.
Oh, yeah.
So anyway, so antiderivative of this guy is just 3. Okay, 3x arc sine y over 3 plus 3y from 0 to 3. And then plugging in some numbers, you get a pretty nice function of 3/2 pi x plus 9. And then you anti-differentiate again, and it's like easy peasy. 12 pi plus 36. The only part of this whole problem that was really that difficult was just knowing this antiderivative. Everything else was actually pretty straightforward. Yes, Tajesh?
What like the antiderivative of the square root of 9 minus y squared? How would you do that?
If it wasn't 1 over, it was
Yeah.
just square root of 9
Yeah.
minus y squared, it'd take trig substitution.
Oh, my suspicions were right. Are we ever going to have to do tricks up in this chapter?
I wrote everything so you didn't have to do any trig sub ever. So I probably have done you a disservice by doing that, but that's how I did it. Yeah, we should.
I did it using the X play,
Mm-hmm.
and then I got a different answer.
Uh-oh. Do you want me to quick try it and see what happens?
Sure.
Yes? Okay. Oh, you know what? Can we do parametrics first and then I'll go back and try it? Just so that, because I don't want to run out of time because we're kind of having fun. I don't know if you guys think projecting onto the XZ is fun, but you know. Okay, so this is just talking about how, in like giving you context and kind of relating it to what we've done before with surface area and mass. But we're not going to do this right now because we've got to get to parametric surfaces, and then we'll go back and see if we can project it onto a different plane. All right, so, this is the one. So we're going to do that same problem parametrically. All right, so last topic of the day. So if the surface is defined by a vector valued function r of u comma v, then the surface integral is given by, so you rewrite your whole integrand in terms of u's and v's, and then instead of the square root of 1 plus z sub x squared plus z sub y squared, it's now the magnitude of the cross product of r sub u cross r sub v. Have you all got the formula written down? I'm not sure where we're at. Okay. if you have to rewrite this surface parametrically, so this is kind of what we started talking about on Friday, was how to write a surface parametrically. Whenever you have to write a cylinder parametrically, do the circle the way that you're used to, right? R cosine theta, R sine theta, and then just let the other input variable be the height, right? So in this case, our x is just the height of the cylinder. So I called it u. And then my actual cylinder itself, well, the radius is a constant of 3, so it would be 3 cosine theta, 3 sine theta. So I get x equals u, y equals 3 cosine theta, z equals 3 sine theta, and now I've generated my cylinder. And then to limit it, first octant, my thetas, this is what we're kind of starting to do in the other screen. My thetas would go 0 to pi halves, and my u's would go 0 to 4.
Could you just explain the whole thing?
Yes, absolutely. Okay, so if I have a cylinder, so a cylinder is basically just a circle with height, right? So whatever your circle is, right, it's some radius r that's given. So some hard-coded radius r, in this case the r is 3, right? Okay, so this is 3. So you just do the equation of a cylinder, or of a circle, so 3 cosine theta, 3 sine theta, for the two variables that your equation's written in. And then the other one, just make the other variable. So you've got one input variable of theta from your circle, and then the other variable can be whatever you want to call it for your height.
Thank you.
And then we had to restrict it because they only wanted first octant. So instead of theta going 0 to 2 pi, we have theta going 0 to pi halves, and our u's, which is basically just our x values, are going 0 to 4. So our r sub u comma theta is this lovely vector u 3 cosine theta, 3 sine theta. You have two jobs. One is to rewrite your integrand in terms of u and theta. So x just becomes u, z becomes 3 sine theta. But then your other is to find r sub u cross r sub v, and then find the magnitude of it. So see if you can take a minute, find your partial u and your partial v, find their cross product, and then see if you can find the magnitude of that cross product. All right, so this is my cross product. I got 0, negative 3 cosine theta, negative 3 sine theta. How do you do with the cross product? That's fine. Okay. Then you got to find the magnitude, which would just be 3 once you square them and add them together. All right. And then you rewrite your integral. So your integral now, remember it was x plus z. So it's u plus 3 sine theta times the magnitude of the cross product, d theta du. Theta is going 0 to pi halves, u is going 0 to 4. Or did you already finish?
You could do d and theta.
Oh yeah, because they're both constants, it doesn't matter. I will tell you in your homework, they give you, if you're doing a surface integral parametrically with the cross product magnitude thing, they give you the parametric definition already. They tell you this is u, this is v, kind of a thing. If you're doing it in just with regular traditional f of x, y, z, then they give it to you that way. So you can, you don't have to do the conversion yourself. All right, so because we have 8 minutes left, let's go back. and try this one. Rishi, you did it with the XZ plane? Okay. So if we do it with the XZ plane, so I'm going to move this over and just work side by side. All right, so the nice thing about the XZ plane is you don't have to change anything in your integrand, right? So if we do it, the XZ plane is this way. So we're projecting, that would be our projection onto the XZ plane. This is still 3, this is still 4. So we would still have, so we'd have to solve this for y, so we get y equals 9 minus z squared, square root. All right, so then you would have the integral of x plus z times the square root of 1 plus, so y sub x would just be 0, and then y sub z, so 1/2 times, let's see, square root of 9 minus z squared is negative 2z, the 2's are canceled. Quantity squared. And then you could go dx dz or dz dx, they're all constants, it really doesn't matter. Did you go dz dx or dx dz? You went dz dx? Okay. So my z 0 to 3, x 0 to 4, right? Okay. Okay, so let's clean this up. So I have x plus z times the square root of 1 plus z squared over 9 minus z.
I forgot what I did.
Oh, you're already okay? Okay. This is going to be kind of a pain. You'd have to find an LCD to clean this up and then see if you can, it's going to be a big pain. So yeah. So, it wouldn't be that bad. It's actually almost the same as this problem. But anyway. Okay.
What was that from? Yeah.
So